All right. So when we started with Ohm's law, where we said V is equal to IR, right? Where we were like the only resistance or the only opposition to the flow of current within the circuit is this R, right? And we did some DC and then we go to AC. And we said in AC, there are some other elements that can oppose the flow of current, right? And then we said for that we rewrote Ohm's equation for AC, where we said V is equal to IZ, right? And because of this IZ here, there are other elements that are in aside the resistor, right? So we end up having aside the resistor, we end up having an inductor, right? And then we have a capacitor as well. Because of this, we introduce a Z here to show that the resistor is not the only element, right? The only passive element opposing the flow of current, right? So this here could represent a combination of these two, or combination of these two, or all the three, right? Yeah, so we saw that. All right, and then we said that because of their characteristics, because we are doing AC, the quantities that change with time are the quantities that change with time that are sinusoidal, because most of our discussion has been sinusoidal waves, right? The quantities that change with time are the voltage, and the current. And we said that when these voltage and current sinusoidal quantities are flowing through this passive element, there's a particular behavior, right? So if you have a circuit that let's see, if you have a circuit that is purely resistive, meaning that the circuit has only a resistor, what it means is that the the voltage and the current are in phase. And we did some pieces, right? And we said they're in phase. We said the length of the line represents the RMS value, and the direction shows as the what do you call it, the phase angle relative to the x-axis, right? Okay. And then we said that when it's purely resistive, when the circuit is purely resistive, only a resistor is present, right? The voltage and the current are in phase, right? Which you can see here, right? And then are in phase, right? Okay, making this right. And then when these quantities, so when we're having a circuit that is not purely resistive, right? But then we have a circuit that is let's see, purely inductive, right? There's also a relationship for that one. And what did we say for that? This is just to help us remember what we are doing. I've said one it's a purely resistive so a purely inductive circuit. What you have is that the voltage leads the current by what, 90 degrees, right? So unlike the purely resistive where we have them in phase, in this one the voltage leads the current by 90 degrees. And then when we have a circuit where it is purely capacitive, right? Purely capacitive means that there's only a capacitor. The only thing in the circuit is a capacitor, right? What that will mean is that we saw a particular relationship for that as well. What we saw was that the current leads the voltage, right? Leads the voltage by 90 degrees. By 90 degrees. 90. Basically, this will be the current, right? This will be the voltage. This is capacitive. This is voltage. This is inductive, right? Most of the times we leave the current just because all the currents are in line here. We go someone see that we are talking about a series current, a series circuit, right? These three are connected in series, but there's just a common relationship between the voltage and the current, right? So let's see. Let's just write VR because they are not on the same phase diagram. We can separate them. This is inductive. This is capacitive. Right. Okay. All right. And then one thing is that because of this, what's the name? Because of this relationship between the voltage and the current for this particular element, there's a particular relationship that shows, right? So let's see. But now let's talk about power, right? But we know clearly that power is equal to I squared R. That's one is only the circuit is purely resistive, right? But what happens? Right, so the same thing as we have V, sorry, the same way as we have V is equal to IR, if the other passive element, we have V is equal to IZ, right? So let's see. The same way, if we have a only resistor in the circuit, the power is written this way. But if the other element, the power is no longer this way, but write it I, and then we have a V, right? So it's basically the same as this, where we have I times IR, right? Something like that. Okay. And then because of this relationship here, right? And how each of them, when there's a, what do you call it, a voltage apply across them, the relationship between the current and the voltage, right? It makes the power behave differently across them, right? So looking at that, for instance, so we know that looking at this, let's see, if it to be purely resistive, right, whatever happens to the current or the voltage is, or the resistance. So let's see, we know for this one right here, for the purely resistive, we have P is equal to IR, right? But if it happens P is equal to I squared plus I squared R, right? So if it happens that the current is negative, that's sinusoidal, as we said, that the quantities V, right? That the quantities V and I are sinusoidal, so we get to some point that they are negative, right? So if for the purely resistive, it happens that the I is negative, right? It will still be the same. Why? Because it's a square. So we end up getting minus 1 squared minus I squared R, which is still I squared R, right? But what happens for these ones? The purely resistive, purely inductive, purely capacitive, right? You see clearly that the voltage and the current are not in phase, right? So it might get to some point where any one of them is negative. So as a result, the power behaves differently. So let's look at the graphs here. Don't be scared. It's not much of anything. We are just using this to understand what's happening. Okay. So let's see. Purely resistive. So you see that at every point, because they are in phase, because we use the sine waves to derive the phases, right? To get the phases. We don't want to be always drawing the, what do you call it? The sinusoidal waveform. So that's why we use the phases, right? So looking at this one, for instance, we see clearly that the voltage and the current, let's zoom in so we see what's up. So now we're talking about the purely resistive, right? Purely resistive. Okay. Now we're looking at purely resistive, which is this one here, what we are seeing here. This, right? So clearly, because the voltage and the current are in phase, that's the purple and then the yellow are in phase, their power behaves in a particular way, right? So you see, let's go over this one more time. Okay. Okay. Then again, feel free to skip this side if you know you don't need it, right? But it's just to help us build understanding and flow. Okay, so let's see. So clearly, because of how the voltage and the current are, they're always in phase, right? So as a result, we have what V is equal to I. Whatever it is that happens, the power will still be positive, right? The power will still be positive, even per the equations, and even if you use you don't use I, sorry, even if you don't use I R, right? You don't use I squared R, and then you choose that's for the power, and you use the IV. We are still on the purely resistive. When you use the IV, the power would still be positive. Why? Because even if both are negative, they cancel, become positive again, right? So that's why for the purely resistive, you see the power is always positive. The power is positive, right? So that's the red graph that we are seeing, positive, right? Even if you pick one cycle of the whole current and voltage, the power is still positive, right? You have a positive power here, positive power here. So this shows that it's actually doing work, right? So why? Because power is the rate at which work is done, right? And what work is the resistor doing? Converting the electrical current to heat, or converting the electrical energy to electricity to heat energy, right? So actually doing work. But when you look at the purely inductive and the purely capacitive, this is what happens. So you see, in this, let's see what's one cycle. So let's see if one cycle is from here to about here. Let's see. Let's see to about here. So this, now we're dealing with the purely inductive, right? So let's see what's happening. So this side here, the power is down, right? This side here, let's go over it first. You see that? Okay, so you see clearly that this side, both of them are negative. So if we have a basically we are doing IV, right, for power, still working on power, right? So you see that at this point the voltage is positive, right? The current is negative. So right, the whole power here is negative here, clearly. So whenever any of them is negative, it tends that it's something changed, right? You see that here, we have the voltage positive, the current positive, right? So as a result, the power is positive in this side. The graph just the waveform just help us to understand and see what's happening, right? For us to see, to get some understanding, right? So here too, current is positive, voltage negative, right? So we end up having the power of negative. So we follow the same thing. So whenever any of them is negative, the whole power is negative, right? Yeah, but there's nothing to cancel out the negative. Take out the negative, right? So positive here, right? And then we have a negative here. Okay, so clearly you see that it's just, so let's see, here's negative, here's positive, here's negative, here's positive, here's negative, right? So somehow, some way, this here is a full cycle. So you see that within a full cycle, it does no work at all, right? Because the power here is negative, here is positive, negative, positive. So basically, it's just doing a net zero work, right? So the same thing happens with a purely capacitive, right? So you see clearly that see, negative here, positive here, negative here, right? Positive here, negative here. This one cycle. There's just another part. This positive, right? So you see, then again, this one too, just like the, what do you call it? The purely inductive, but kind of like flipped around the x-axis, right? Or rotated around the x-axis. So that's it. So then again, positive work, negative work, cancel out. Positive work, negative work, cancel out, right? Positive work. So basically, these two are not consuming anything from the circuit, right? So they are theoretically they're just doing a net zero work, right? So there's not actually work done, which so we don't so there's no rate at which the net rate at which work is done, so they don't convert the electricity to anything. So they convert, so for the inductor, it stores the electrical energy in its magnetic field, then again in the other half it gives it back to the circuit, right, or to the source. The capacitor does the same, it stores it in the electric field, gives it back, right? So there's no network done. So you can actually see clearly that the rate of work, the rate at which the electricity is converted to heat in the resistor is actually a work done, right? So whenever we see something like that, what it means is that a work is being done. And one thing we see about that is, let's see, minutes, because work is being done, it means that the resistor is being what, let's use this term, active, right? So the power here is active, right? Because whatever it is that happens, it does a work, right? Converts that kind of electricity to heat energy, right? So we see the work there is what, the power there is what, active, right? So let's go over this one more time. It means that the power is what, active. The power is what, true, right? That's if the circuit has only a resistor, right? The power is active, the power is true, the power is real, or you can just say power. So it's just either active power, true power, real power, or just power, right? Okay. So let's keep this one. It's active, like it's actually doing something, right? It's converting the electricity to heat energy, right? Okay. But when it comes to these ones, the purely inductive, a purely capacitive circuit, the only thing that they are doing is that they are just the what do you call it? The energy is being given to them and they give it back to the circuit, right? So basically what it means is that they are being reactive. So that when you have a circuit that's having any one of these alone, so it's either having only an inductor or a capacitor, we see that the power there is what, reactive, right? Reactive power. And then there are names that we use to describe these two. Because they are names, there must be a symbol that we use to make things easier. So let's see. So you see that you're having this one is for purely inductive or purely capacitive, right? And this one, these names here are for the power that the purely resistive consumes, right? So the purely resistive consumes only active power, right? And the purely inductive or the purely capacitive consumes only reactive. Sorry. So the purely resistive consumes only active power, and the purely resistive consumes only active power, which has all these other names. and the purely inductive or purely capacitive consumes only reactive power, right? Only reactive power. And then there's the thing we have it. But think about it. What will happen if a what do you call a circuit not only have a resistor, right? But it either has, let's see, resistor, inductor, capacitor. So what happens if a circuit does not only have a resistor, right? But could be a combo of these two, or a combo of these two, or a combination of all of this, right? So the power that the circuit will have to produce for them to do their work will be a combination of this real power here, this active power here, and the reactive power. And whenever a circuit is that way, having any of these two, including R and any one of the other ones, either inductor or capacitor, we see that the power there that there's what do you call the circuit is producing for them to consume, right? It's what we call an apparent power. Apparent power. And what this shows is that the apparent power will compose of the apparent power will have an active part, right? And will have a reactive part. So that's what it says. That's when you have a circuit having these two, right? Any combination of these two, whether resistor and inductor, or resistor and a capacitor, or resistor, inductor, capacitor. To have that will mean the power will be apparent power, and to have both this active and reactive power, right? But then let's see, there are symbols that we use to represent this. As you can see, active power, we said is true power, real power, or power, and as a result, the symbol that we give for this one is just P, right? This active power is just P, and the symbol that we give for the what do you call it? The reactive power is Q, right? Q. Okay. And the symbol that we give for the apparent power is S, right? And then someone will ask, what about the unit? The units are a bit different, but it's just the same thing. When it comes to the power, which is this one, the P, right? What happens is that the unit for that one is just W, which is watts, right? Watts. So just the symbol is just W. Okay. When it comes to the unit for the reactive, that's what we have. A minute. The unit for that, is we say VAR, right? So that's what's the name? Volt-Amperes, because you know power is what? Let's go over this one more time. We know power is equal to, if it's purely resistive, I squared R. But if it's not, V is equal to what? IV, right? So this is basically volt ampere, right? Current, what do you call it? Volt, right? And the units are amperes and volt respectively, right? Which is the same as P is equal to VI, right? So, sorry, VI. So we have volt and we have amperes, right? So the unit that we give for this particular reactive power is volt-amperes, but what particular kind? The reactive kind, right? What is still volt-amperes, but we give it a particular name, right? But then the reactive power, we say volt-amperes reactive. So there's the unit for it, right? If it's plural, more than one, we just add an S, right? If it's more than one, we add an S, right? Okay. So let's see what var, right? And for this apparent power, which composes of this and this, what we just say is that because we don't know whether it's reactive or it's active, the unit we give for that one is just what? Volt-amperes, right? Just V I. So this one, just write it as VI or volt-amperes. VA rather. VA. Just VA. Right. So VA. Volt-amperes reactive. This is just volt-amperes. So we don't know the kind of power it is. The apparent one, that's why we just say volt-amperes, which is voltage and current, right? So volt-amperes, that's a unit for them. All right. So now that we have all this understanding, let's see. Another thing that we must notice is that let's see. So now we've seen clearly that these are related, right? And that you see clearly that these are related, and that we know that the true power and the reactive power are all parts of the, what's the name, the active, the apparent power, right? That happens when we have a circuit that has both what do you call it, resistor and an inductor, or resistor and a capacitor, or we have all the three, right? So that's what happens for these ones. Okay, but there's some other thing that we must make note of. So let's see, we're just going to go over that. So we know that these two, active and reactive power, are part of the apparent power, right? As if you have a circuit that has the combinations that we've said. Right? So let's see. Another thing that can happen is that there's a particular relationship between these three, right? So if it happens that the circuit has these three, so we know that, so let's go over this one more time. There's something that we must get understanding of before we proceed. Let's see. Okay. Then again, if you feel this particular side, we're going to solve an example, but if you feel this particular side you don't need it, you can skip over it, right? That's the essence, that you are able to choose which one you feel or you know per the whatever it is that you are doing you need, and which one, the ones that you don't need. It makes your work easier. But then we are trying to connect everything that we've done to get some sort of flow in what we are doing. So let's see. So when we were doing the RLC, the resistor, inductor, capacitor, we said that because of how the voltage and then the current are in them, we have a particular diagram that we use. We have something like this. Let me just do this. So basically we have this, right? And then we have this. This diagram help us to understand the relationship between the current and the voltage in them, right? So here we have a capacitor. Okay. Right. And then we said here is a resistor, inductor, capacitor, right? And that, okay. And we know that if current were to be here, right, the current for the resistor, the current will be in phase, be in the same phase with the voltage across the resistor, right? And then for the inductor, the current will be 90 degrees, right? Meaning that the voltage leads the current, and then the capacitor, the current will be 90 degrees to it, but then the voltage lags the current, right? So this is what we are using. The same thing happens, right? And we said that the resistor is related to power, which has a unit of watt. And we said that the inductor, capacitor are related to what? Reactive power, which have a unit of what? Differently. So for inductor, let's do this one now. Right. So the inductor is related to reactive power. The capacitor is related to reactive power, but then the units are different. This has a unit of the inductor, right? So the reactive power still has the same unit, which is what's the name? Volt-Amperes Reactive, right? Okay. But then we said that when we have any of this combination, whether R and what's the name? R and then inductor in the circuit, or R and then capacitor in the circuit, or any of all these three, then we end up having what? Apparent power, right? But then we're going to draw a relationship here to see what's happening. Okay. What happens is that the resistor only consumes power. The inductor consumes only reactive power. The capacitor doesn't consume any of them, but it makes sure that it reduces the consumption of the inductor, right? The what do you call it? The reactive power consumption of the capacitor, of the inductor, or it supplies the reactive power. That's what it does. Okay. So let's go. We are going to see the relationship between these ones. So let's see. What happens is that there's also a similar relationship between the active, reactive, and the apparent power, right? And we are going to look at that. Okay. So what happens is that, what did we see? We said that okay, we said that the resistor is the only one that consumes, what do you call it, active power or power, right? So what that will mean is that we end up having the active power here, right? And then we said that the inductor consumes only the reactive power, right? So the inductor is here, right? So it ends up showing over here. So that's this is where we have the Q, right? There was the Q. The other thing is that what we are saying, and these are vectors, right? Because they are voltage and current assigned, so that then the power and then the powers, which is the active power, reactive power, will be sinusoidal and as a, and because of that we can have phases for them, right? So these are just the phases for them: active power, reactive power, and because we are doing vector sum, we end up getting a resultant, which is the, what do you call it, what we call the apparent power, right? Which is the S, and because of that there will be a phase difference, right? A phase difference. But what happens is that mostly when it comes to AC, we do a relationship between the power or the true power, active power, or the other name that it has, and the apparent power, because what we see from the graph, the power is basically the one that done that does the active work. Right, so let's see. So we have something we call a power factor, right? So basically we know that there could be a phase angle here, right? The phase shift, right? And that phase shift helps us to relate the apparent power and the true power. And what we say is that, so let's see. So clearly we know that if the moment we have apparent power, meaning that there's some form of true power in it and there's some form of reactive power. But then looking at this one very well, and as we've been doing with the resistance and impedance and everything, we know clearly that this one here, the P is on the x-axis. So if we want to find the portion of this P that's in the apparent power, we use cos, right? Because we have some sort of triangle here, right? So we can do some Pythagoras. So that means that this P here, let's see, P is a part of S. And how do we get P? Just do this one. So we know that P is a part of S. Is a part of S. It's related to S. And how do we get that? We use cos. Cos of what? This phase difference here, or the phase angle, because they are phases, right? So cos this theta here, right? It could be anything. Some at times you can even see it as this, this, right? This. So what it does is that this power factor that is able to tell us which amount of the apparent power is active, right? So that's what it shows. So the active the what's the name? The power factor itself is the whole cos this, right? So if you are trying to find that, that will mean that the power factor, which is the cos theta, is basically the S, so basically the P on the right on the S, right? So that gives us the power factor, right? And we know clearly, let's go over this one more time. And we know clearly that, so this here is the power factor. So let me write somewhere that the cos theta here is the power factor. It's not fitting. Power factor. Which at times you see it as just PF, right? Power factor, right? Right. So we know what the cos theta is now. Another thing that we know is that when we see power, meaning that the only thing that's in the circuit is what, or the power relates to actually relate to the resistor, right? So that means that we have a I squared R, right? I squared R, I squared R, which is the same as yeah. Let's just say I squared R, right? I squared R. So whatever it is that happens, the moment you remember this one here, based on the parameters that you have, you can find the other ones. Or right, you remember this basic one, and it helps you do it. We know power is related to resistance, so I squared R. And we know this one, this S here is apparent power. That means that we don't know whether we're just saying the, what do you call it, the resultant sum. The circuit could have either resistance and inductor, or there's a name, resistance and capacitor, all the three of them, right? So that will mean that we just use a IV, right? So whatever it is that happens, just remember the basic one, and then you'll be able to find a way around it, right? So this is basically I and V, right? Or I and V, right? I and V. And then at times what happens is that because of this resistor here, and then we said that the power is only relating to the resistor, but then because apparent power is in, meaning that we could have resistor and capacitor and all the other elements, right? So all the other passive loads, so we can end up getting something like what's the name? I C, and then something like Z squared, right? I squared, sorry, this should be I squared, and then Z, or I squared, and then R. And if they are in series, then we can cancel. That's if and only if the elements are in circuit, then we can cancel this I because the current will be the same, and we end up getting just R on Z. Right? So that's it.